Now I welcome our next speaker, Dr. Dept, Assistant Professor at University of Louisiana at Lafayette in US. He had been postdoctoral fellow, Faculty of Dentistry at McGill University, Montreal, Canada. He served as a research scientist in University of Louisiana, Lafayette. He has 18 peer-reviewed publications with 2,640 citations. He has delivered 11 invited talks in various conferences and worked as principal investigator in many research projects. He received the prestigious Board of Regents and Professorship Award 2016 and 2019. and Dr. Wallung Award 2009 from McGill University, Montreal. NSERC Postdoctoral Fellowship by Government of Canada, International Travel Grant Award from Institute of Nanotechnology, Scotland, UK. He is member of editorial board of various journals and Royal Society of Chemistry, London, the Metals, Minerals and Materials Society USA, Society of Polymer Science Pune, and Society of Biomaterials USA. Now I invite Dr. Dept for his valuable talk on polylactic acid crystallization induced by carbon nanotubes, microstructure and degradation. Welcome, Dr. Dept.
Can you hear me?
Yes, sir, you are audible.
Okay, thank you. First of all, thanks for the nice introduction about me. I'm feeling very good. First of all, good morning to everyone. I know it's kind of a late night here, and for Amit also, but I'm feeling so nostalgic by presenting in the department. I graduated 20 years ago. So it cannot be, you know, like a better proud moment for me to present for the department. So let me share my screen first. Just a minute. How do I share the screen? Share screen. Okay, can you see the screen?
Yes, yes.
Okay, that's great. So first of all, thank you for inviting me. And when Ms. Kavita and Ms. Suchitra spoke to me, then I was a little bit skeptical about the theme of the webinar. And then I thought maybe I can dig something relevant. And then a topic on a biodegradable polymer came, and then I thought I think it might fit very well within the theme of the seminar. So here today I will present my recent research that we have been doing in the past couple of years. And so my talk will be kind of a more like a research article. So let me go to the presentation slide. Okay. So here, if you look at the map here, that's where we are located in the southern part of USA. So we are somewhere in between the Houston and New Orleans. You might have heard about the Hurricane Katrina that devastated New Orleans, and the famous city Houston, which is famous for NASA. So that's where we are located, is somewhere in between, and that's College of Engineering building. We have around 6 departments in this college, and this is the University of Louisiana Lafayette is the second largest state university in Louisiana, and our department is the second largest after mechanical engineering with around 12 faculty members. And I joined here in 2016 as a tenure track faculty member, and the work I'm going to present is we started doing like a couple of years ago only. So I'll cover the polylactic acid. It is actually a compostable polymer. It's a compostable and biodegradable polymer which is derived from renewable sources like cornstarch, sugarcane, etc. And is there any issue here with sharing screen?
No issues, sir.
People are sharing, raising the no issues. Okay, okay,
No
that's
issues.
great. So, no, I heard some noise thing. So, okay. So it's a compostable bioplastic. It is primarily made from corn, and primarily made from corn in the United States. It is a compostable wherever the facilities are available, because not many polymers they can be composted in a household facilities. So it is compostable where the facilities are available. Okay, and it is also a biocompatible polymer. That means that it's a non-toxic, and it can be used for many biomedical applications. And so the disposing of polylactic acid in a landfill is also an acceptable end-of-life option. Okay, so coming back to the properties and applications. So PLA is a water insoluble polymer, and it is optically clear. Requires 60% less fossil fuel to produce than most of the conventional or petroleum-based polymers. Its properties are also comparable to the PET-based plastics. So it has a huge potential in food and packaging applications because it has a good barrier properties and good physical-chemical properties. So and it also can be used in various biomedical applications because of its non-toxicity and low immunogenicity. Okay, so however, despite of all these many applications and advantages of polylactic acid, there are some limitations. So it is difficult to crystallize. First of all, the biggest disadvantage with polymer is that it is difficult to crystallize this polymer. It is primarily in its amorphous state. So the amorphous domains means it will have a poor or inferior mechanical properties, such as inherent brittleness or lower toughness. So to mitigate these kind of problems, what we can do is we can use different type of nanomaterials. So, or maybe simply say nanoparticles. Nanoparticles such as carbon nanotubes or graphene or clay. If you use these kind of nanoparticles, then we can improve, we can not only improve the mechanical properties, but we can also control the degradation. Now, many of you might be kind of confused or wondering that the polylactic acid is a biodegradable polymer. Okay, so and the theme of this webinar is advancing climate change. So if we already have a biodegradable polymer, then what is the use of controlling, or what is the advantage of controlling the biodegradation? Well, there are several advantages. For example, and I'll talk that later in my presentation, that by controlling the degradation, you can, for example, the polylactic acid is being used for food and packaging applications. So if you control the degradation, you can control the shelf life of the food that has been packed inside. Okay, for various biomedical applications, you want to control the degradation because you want the polymer to stay there or inside the body up to up to the time you want it. And then since it is a biodegradable polymer, then it will decompose inside the body, or it will resolve into the body, leaving no toxic residue. So that's why the controlling the degradation is of paramount importance. So how can we control the degradation? So for that, I just mentioned that we can improve the thermomechanical properties by use of various types of nanoparticles. So you can use pretty much any nanoparticle, whether it's in the form of a nanofiber or nanoplatelets. You can use quantum dots or carbon nanotubes, which are also very popular. So you can pretty much use any type of nanoparticle. So all that you need to do is just either melt mix with the polymer, or you can disperse it into a solvent and then mix it with a nanoparticle to make polymer nanocomposites. Okay, so among the different type of nanoparticles, carbon-based nanoparticles are the most prominent ones, because they are easy to make and they have very good properties. Among them, the graphene, which is considered as a mother of all the graphitic forms of carbon. So these various polymorphs of carbon, for example, carbon nanotubes, whether it's a nanodiamond or graphene, fullerenes, these polymorphs of carbon, they exist from 0-dimensional to 3-dimensional structures. Okay, and because of their small size, they have high specific surface area, and also they have the large aspect ratio. So because of these properties, you don't need to add a lot of these nanoparticles. You can just add a very small amount, maybe 0.1%, or sometimes at the max, I would say 3 to 4% by weight should be enough to improve the physical properties of the polymers. So when you add these nanoparticles with the polymer, what you get is a polymer nanocomposites. So among the first type of the nanoparticles that we use is the carbon nanotubes. These are also very popular ones because they make lighter, stronger, and tougher materials. They can be easily made at a large scale. They are cheaper. You can make them highly pure. You can functionalize it the way you want to add to a specific polymer. So because of all these advantages, the carbon nanotubes, they offer several advantages over any other traditional nanoparticles. Okay, so coming back to the issues with the polylactic acid. So the screens on the screen, you can see the advantages of the polylactic acid. We know that it's a renewable source materials, biodegradable. It is optically transparent. However, its cost is 3 times of the biodegradable polymers are very young candidate or a very young material among all the polymers. Okay, so the biodegradable industry is in a very infant stage. So as there will be a lot of investment or a lot of research on biodegradable polymers, I'm hoping that the cost will go down, and then those days are not very far when these biodegradable polymers will replace the petroleum-based polymers. However, for the full exploitation of these polymers, especially the polylactic acid, we need to fix a couple of issues. For example, we need to improve the thermomechanical properties, the slow crystallization. The polylactic acid is very difficult to crystallize. Okay, even though if you crystallize it among the most optimum conditions, the amount of the crystalline polymer will be very less, and polylactic acid is also brittle with a low modulus and hardness. So all these issues that needs to be fixed, and then me and my research group, we have been exploring the various methods how we can improve the properties of these polymer nanocomposites. So we first figured out that can we improve the crystallization of polylactic acid? That's the biggest issue. So among the crystallization, if you follow the fundamentally, it is based on two steps. The first is the nucleation and the growth. So if you are using a heterogeneous nucleating agent, for example, carbon nanotubes or any nanoparticle, they lower the activation energy, and so increases the rate of the crystallization. And by that, we can control or we can manipulate the properties of this polymer by manipulating the microstructure and the microscopic physical properties. Okay, so we used carbon nanotubes, and then I think I jumped one more slide. Okay, so in this slide, you can, so what we did is it was a very simple method. We added carbon nanotubes with polylactic acid, and we used a solvent to mix both of these, and then mixed by melt mixing to make sure that the carbon nanotubes are dispersed very well within the polymer matrix. Okay, and then we studied various physical properties. Now in the FTIR spectra proved that there is not a significant changes into the chemical structure, so which is okay. However, if you look at the DSC data, put this here. Okay, so if you look at the DSC data of a pure PLA, you will see a small hump at around 70 degrees Celsius. Okay, that is due to the relaxed enthalpy. Now, relaxed enthalpy is due to the amorphous domains. So the amorphous domains of the PLA will be there. Then those amorphous domains will show a relaxed enthalpy at around 70 degrees Celsius. Now, if you look at exactly down on the PLA CNT nanocomposite, you will not see that hump, which is indicating that we do not have amorphous domains on PLA CNT, confirming that the carbon nanotubes have improved the crystallization of polylactic acid, and then it helped the amorphous domains to be primarily in the form of a crystalline polymer chains, and that's why we did not see the small hump at around 70 degrees Celsius. Okay, now keeping in mind that the theme of the webinar, I have removed most of the other studies, and then I kind of focused mainly on the degradation aspect and how to improve the mechanical properties of this polymer. I kind of focused mainly on those aspects. So here I presented the degradation. So what we did is we used a UV chamber to mimic the photo degradation and the photo or hydrolytic degradation of this polymer. Okay, so in that UV chamber we have the UV light, and then with the water controller we can control the moisture. So the polylactic acid is degrading in the presence of a UV light and moisture. Okay, so by that way we are mimicking the actual environment where these kind of polymers, if they are going into a landfill, these kind of polymers will be exposed to. Okay, and then we irradiated with the UV lamp for 100, 200, and 300 hours, and then we performed most of our studies. So in this one, you can see the scanning electron micrographs. So it is very clear that as the irradiation time or the degradation time increased, you can see various voids or the various pores or the holes on the surface of this PLA specimen. Now, polylactic acid is a polyester. Okay, so and we know that the polyesters, they degrade by hydrolysis. So if the water is present there and the ester bond cleavage, it starts from the surface. So that's why you see numerous voids and numerous pores only on the surface. Okay, now here you can see a comparison or a direct comparison between the degradation of polylactic acid and PLA CNT. So here it is very clear that the presence of carbon nanotubes have kind of a controlled the degradation of a PLA. Okay, so the number of the holes or the number of the voids and the pores are smaller in the PLA CNT. Okay, and it is primarily because of the carbon nanotubes. Now, carbon nanotubes, if they are uniformly dispersed within the polymer matrix, they can resist the penetration of a UV light. Okay, they will also create a mesh or a web-like structure inside the polymer matrix to create a tortuous path that will prevent the penetration of the water molecules. So if the UV light is not going inside, or if the water molecules are not going inside, what you're doing is you're basically controlling the degradation. Okay. Okay, so here it is in a schematic. It is clear that the CNT is because of the tortuous pathway, it can control the degradation of this polymer. Okay, I think we can skip this one. Okay, now the mechanical properties. So we used a nano indenter. Now it's a nano indenter is a very unique and a highly sophisticated equipment. So it has a nano probe of diameter less than 10 nanometer, and then we use that probe and then we insert it inside the specimen. Okay, so if it goes inside the specimen and then it records the load versus displacement data. Okay, so if you might have studied in maybe in the high school or in college, the load displacement data or the stress strain diagram. That's what the role of this nano indenter is. So if you look at the left hand corner on the bottom, these are the two images of the nano indenter. It has a very, very small probe, and then with the stage, it has an automatic stage, and then we need to just mount the sample, and then it goes inside, and it has a diamond probe, and then it hits the sample and then record the load versus displacement data. Okay, so ideally it gives you an indication of how strong the material is. If the material is stronger, then you will see an improved data or the improved load versus displacement data. Okay, so it is very clear. You will see some very interesting data here. Okay, so if you look at pure PLA, let's first look at the pure PLA. So we can see, first of all, we can see that there is a slight increase in the modulus and hardness when we add carbon nanotubes. Okay, even though it is not much, we expected a kind of a significant increase. However, we did not receive a significant improvement in this data by the addition of carbon nanotubes. So it might be because of several reasons. First of all, carbon nanotubes, they are highly hydrophobic. They have a very strong van-der-Waal interactions. So they have a natural tendency to agglomerate. So when they agglomerate, you will not have a proper dispersion of your nanoparticles inside the polymer. So you will not get a uniformly distributed matrix. So you cannot expect very good improvement in the mechanical properties. So the first thing is that there is not a significant improvement in the modulus and hardness by adding carbon nanotubes. Okay. Secondly, if you look at the data from pure PLA, as the time proceeded, you will see an improvement in the modulus and hardness, right? But however, if you look at the data for the PLA CNT, the data is kind of more stable. Like the modulus and the improvement in the modulus and hardness was kind of a more stable. It's like a flat line. So we were kind of surprised to see that data. We thought that it might be just the opposite, but however, we did it several times, and then all the time we got the same data, and then it made us really curious to what's going on. So then we figured out that it is a process of chemicrystallization. So what is chemicrystallization? I will explain in a layman's language. So this is the polyester. It's a hydrolytic polymer that undergoes hydrolytic degradation. Okay, so hydrolysis will break the PLA chains into smaller, maybe into low molecular weight oligomers, or sometimes even low molecular weight monomers. Okay, so these small chains of low molecular weight, they have a very good tendency to crystallize again. So even though they are in the polymer matrix, these broken down chains of polylactic acid, they will start to crystallize again. Okay, and once they start to crystallize again, they are smaller in size. They will make a very compact lamella. They will make a very compact crystal. Okay, and the compact crystal, when it is tightly packed, it makes the material more brittle. Okay, so we thought if the PLS-CNT, if the CNT is controlling the chemicrystallization, it might be a good idea, because here the carbon nanotubes are controlling the degradation in such a way that they are also controlling the properties. They're not allowing the chemicrystallization. Okay, they're stopping the chemicrystallization to occur, or maybe not to that extent. Okay, so this application, this particular data is very important, because this feature can be used for many tissue engineering applications. So PLA is a biodegradable and biocompatible polymer. It is used in many tissue engineering applications. So to repair the wound or as a suture. So for a suture, you may not, you would expect the polymer to sustain the degradation in the beginning. Okay, because your wound is fresh, you don't want the suture just to dissolve quickly. Okay, you want the suture to resist the degradation in the beginning of the surgical procedure, and you may expect that the polymer should degrade gradually without leaving any toxic residues. That's what the PLA will do. And here, what is happening is the carbon nanotubes, they are controlling the degradation. And as I explained in the beginning, that controlling the degradation of a biodegradable polymer is why it is so important. Okay, so the carbon nanotubes, they not only improved the mechanical properties, but they also controlled the degradation, controlling the chemicrystallization. Okay, this slide is not very relevant. However, if someone is working, I included this because we are kind of exploring this feature of this nano and enter. Those who are working in comparing the nanomechanical and micromechanical properties, I think they will understand this. So I think I will let me skip this this one and go to the next slide. Okay, so next to the carbon nanotubes, we are interested in exploiting a very unique and a very interesting carbon nanomaterial known as a graphene nanoscroll. So it is a very new nanomaterial. I think if you see the research papers that has been published, I would go like 8 to 10 years from now, where the graphene nanoscroll research has been started. So ideally, all these are graphitic forms of carbon. Okay, so if you consider graphene is like a flat sheet. Okay, flat sheet of carbon. Okay, so if you roll a flat sheet of graphene, it becomes carbon nanotubes. Okay, you take a scissor, like a hypothetical scissor, not an actual scissor. You take a hypothetical scissor and cut it down, that you get a graphene. Okay, so graphene nanoscroll is nothing but a scrolled version of graphene. Okay, so I will explain you exactly how we made it. It's really interesting. So they are formed by rolling up the layers of graphene, and they also have the open-ended topology with a significantly more accessible interval area. So unlike carbon nanotubes, which has a closed end, the graphene nanoscrolls is open from both the sides. Okay, so where the polymers or or other small molecules or the gas molecules which cannot penetrate inside the carbon nanotubes, now we have a better version of graphene, which is graphene nanoscroll. It is a tubular structure with both the open ends. So its surface area is several times higher than graphene and carbon nanotubes. Okay, in fact, the specific surface area of graphene nanoscrolls that we synthesized was of 400 meters square per gram. That's a really high surface area. Okay, for a graphitic carbon. So ideally what we do is we take graphene and then we apply ultrasonication. So ultrasonication will create a lot of stress on the edges of the graphene, and then we immerse it immediately into liquid nitrogen. So liquid nitrogen will create a lot of stress on the edges of the graphene, then it will start to scroll. Okay. Now you might be wondering that if when the liquid nitrogen is gone or evaporated, why doesn't it comes back and unroll back into graphene? No, it doesn't happen because of the strong van der Waals interactions and strong pi-pi interactions. What happens is it keeps on scrolling, and then and it will not allow you to unscroll it back. Okay. So that's how we synthesized these graphene nanoscrolls, and we thought that it might be easier, but it took 6 to 8 months to figure us out exactly how to convert the graphene nanoplatelets into graphene nanoscrolls. So here in the morphological analysis, I think it will make clearer to you on the SE and the scanning electron micrographs, the planar or the flat graphene nanoplatelets, and they are converted into graphene nanoscrolls. Okay. And if you look at the high resolution TEM images, then also you can see the scrolled version of graphene. So we used graphene nanoscrolls in this study to crystallize polylactic acid, and then we thought it might be a good or it might be interesting to compare between the carbon nanotubes and graphene nanoscrolls. Okay, so in carbon nanotubes we obtained spherulites. Okay, however, in the case of graphene nanoscrolls, we obtained a flower shaped or a petal shaped structures. Okay, this is because of the large surface curvature of the graphene nanoscrolls. Okay, let me go to the next slide. Okay, so here you can see that the graphene nanoscroll is actually considered as a supramolecular structure. Okay, it has two diameters. Okay, so it has a smaller diameter and a larger diameter. So that is the reason it has a really high specific surface area where that can be exploited. Okay. Now in the crystal structure, we used X-ray diffraction method to exploit the crystal structure of polylactic acid and PLA-GNS. So here you can see that the PLA-GNS has a little bit sharper peak, so that means that the crystallinity has been improved. Okay. However, the crystallinity was increased only by 5%. Now this feature is also very interesting, because in the case of carbon nanotubes, the improvement in the crystallinity was around 22%. Okay, so we expected that the graphene nanoscroll will give us significantly higher crystallinity. However, the difference in the crystallinity was not much. Okay, so we thought that we may not get a significant improvement in the mechanical properties. However, it was really very interesting to see that the elastic modulus of PLA-GNS was 6 times that of PLA, while the hardness was around 10 times. Okay, so there's a significant improvement in the nanomechanical properties. So this is a really interesting data, and we are currently comparing the nanomechanical properties of PLA crystallized with carbon nanotubes, graphene nanoplatelets, and graphene nanoscrolls. Okay. However, our initial data indicates that there is a significant improvement in the mechanical properties, and this is primarily because of the residual strain that is generated during the scrolling of these layers. Okay, so this additional strain has to be overcome by applying extra stress on this type of material. That's why it has a higher nanomechanical properties. Okay, so I will not take much time here, and then I will try to conclude here that polylactic acid had some issues. Obviously, it's a renewable source material, biodegradable, optically transparent. However, by the use of carbon nanomaterials, we enhanced or improved the thermomechanical properties. We solved the problem of slow crystallization, and then we improved the modulus and hardness of pure polylactic acid. Okay, so in conclusion, we used different nanomaterials, and then we try to see how it can improve the various physicochemical properties. And then we compared two materials, carbon nanotubes and graphene nanoscrolls, and then we found that the graphene nanoscrolls are much better than carbon nanotubes, especially in terms of improving the, not in the terms of improving the crystallinity, but at least in the terms of improving the nanomechanical properties. Okay, and our current work is on refining the structure of graphene nanoscrolls, because so far we do not have a great success in a fine tuning or controlling the diameter. Okay, we are also testing the barrier properties, because that's the end application. Polylactic acid is used mainly for food and packaging applications, so we need to test the barrier properties, and also degradation studies for polylactic acid and graphene nanoscrolls. Okay, so we started this work in 2018, and we have, because of the hard work from a lot of my graduate and undergrad students, these are the publications we received from this work. And this is some of the snapshots from my students. So the first one, the Kemi Ajala, she was the first graduate student. She's the one who started this work. And next is the undergraduate student, Caroline Werther. And they both won several awards presenting this work. And I would like to say thanks to Dr. Shidon and Dr. Khattab for my research, kind of research mentors, and my research sponsors for this work. And thank you all of you, and I'm ready to take any questions you might have.
Any questions from audience?
ये देखो ये चैट नैनो पूछो
Sir, there is one question in chat box for you.
Okay, let me see. How do I see that? Let me see.
Nanocellulose may be good potential in this area, as it has unique properties like biodegradable. I think they have only commented on it.
Yeah, so it's really a good comment. It's really a good comment. I would like to comment on that. So yes, nanocellulose. We did some work on nanocellulose also, and then currently we are using nanocellulose with the concrete. Okay, but yes, I think it might be a really interesting to see the effect of nanocellulose with polylactic acid. Technology or
ठीक है, thank you for that.
Thank you, sir, for giving very informative talk about PLA, polylactic acid, a biodegradable polyester, which can be a replacement for petroleum-based plastic. It is really a demand of time, as today we are facing acute problem by the long-lasting nature of plastic with its non-biodegradable property. The discovery of PLA will allow us to design environmental-friendly packaging material. Thank you once again, sir, for giving your valuable time, and we understand that it is a little bit odd us at your place, but your cooperation was enthusiastic. It is really a point of prestigious that today a student of our institution is a speaker of our international webinar. Really a proud of moment for us.
Thank you.
Welcome.
It's really a proud moment for me also.
Thank you. Welcome, sir.
Thank you.
Registration is showing a great overwhelming concern of participants in this international webinar and environment. We have about 780 participants join all over the globe, and still this number is increasing.